Let's say that in addition to the name of the job, maybe we had a file handle or a generator expression or something that was deeply stateful. So we'll put into this thing maybe something that's deeply stateful, like a generator expression. Really simple. The moment we do this, what we'll discover is the generator expression cannot be pickled. A lot of things can't be pickled. Anything that has deep state associated with it, well, there's no way for us to serialize that to some byte stream and then reconstitute on the other end. And as a consequence, there are certain things that we simply cannot share. In a threading.thread program or an async IO program, there's really no limitation to what we can share between the individual computational units. It's only the case that we have to make sure about locking. But in a multiprocessing circumstance, well, we actually simply cannot share things. And not just maybe esoteric things like generator instances, even very regular things like file handles, maybe even certain C objects, anything where that state cannot be reconstituted trivially on the other side, anything that does not support the pickle protocol. Additionally, just because we can pickle it doesn't mean it's going to be efficient to pickle it. Pickling is a relatively inefficient thing to do. For a very large data set, it's going to be costly for us to convert a pandas data frame into its pickled format. If we were to take a look at, say, a relatively large pandas series, so let's do this. Let's do numpy random. Let's do a default RNG. We'll grab from our utils our timer. And let's grab from pandas, series, and to make this interesting, let's do a multi-index with a date range. Like that. Let's create our default RNG. And let's create a not altogether too weird looking pandas series, just something where it has a multi-index and it has some data on that multi-index. And the data here I don't really care that much about, so here I'll just do normally distributed data of the size of however many elements I have in my index. And I'll round them to 2 decimal points because I don't really want to make this too ugly. And then for my index here, let's do this. A pandas series or a pandas data frame can be pickled. In fact, pickling may be the only way for us to store to disk a pandas series or a pandas data frame while capturing all of the aspects of this structure, such as the naming of the columns or the naming of the dot index. But I don't think this is going to be very efficient. So let's do this. Entity or date and entity. And we'll do, this should be from product. And here we'll say a date range. Make this thing relatively large. So we'll say maybe 90 days. And for each one of those 90 days, we'll have one entity. So let's do rng.choice, ASCII lowercase, and let's do maybe 100 entities to start with. And each entity will be 8 letters long. So there we go. So if we look at this series, this is just, and here let's, no, actually we have everything here, so we just need to set the name. Okay, very good. Let's do that. So, oh, and we have a missing, this should be names. Okay, very good. So we just have something that looks like this. And we have 9,000 rows. Maybe we'll expand that in a moment. Let's see how long it takes to pickle this thing. So we can do a 2 pickle here, or I can just do a dump s. Which will do largely the same thing. And I'm actually going to print something out here. I just want to see how many bytes this thing requires for how many rows this thing happens to be. So let's pull in dump s from pickle. And let's see how long it takes to just pickle this thing. This thing's not even that large, like 9,000. Okay, let's grow this a little bit. Let's say we have 100,000 entities for 90 days. So now we're talking about 10 million rows. That's actually pretty slow, 0.2 seconds to just turn this into a pickle. Remember, we have to pay this cost on both sides because we have to pickle it on one side and we have to unpickle it on the other side. So here, what we're going to do is I'm going to dump S this thing. And in addition to that cost, we also have to pay the cost of transmitting this from one process to another, which means copying it from user space to kernel space and then down to user space again. And so we're going to discover that the cost of moving data around in a multiprocessing program can oftentimes swamp any of the gains that we get from being able to have multiple independent computational units. In total, this is 0.2 seconds for 9 million or so rows, and that's just copying this thing around. And if we had multiple processes, we're going to have to copy this to multiple different places. So think about it. If we had 10 processes, that's going to be expensive. Let's actually see what that looks like. Well, what we can do is we can say from multiprocessing, import process, and a queue. And what we'll do is we'll do just something very, very simple. We're going to time the overall run of this program. I'm going to leave this intact for you. We'll create a pool with maybe 10 processes. And some target. We'll give it a shared structure like that. We'll create 10 of these. We'll start them up. And we'll join them. To get a quick benchmark before we share any data, why don't we do the following? We'll just time this by itself. And here the shared is this multiprocessing.q. And we'll actually remove that from our timing. So 0.02 seconds to do more or less nothing. Now, let's do the following. Let's have just one of these be a, have one of these be a creator. Here we'll do like a flag. And we'll say if flag. So only one of these will actually do anything. So we'll do the right. And what we'll do here is we'll do shared dot put, and we'll put this thing here. I'm going to actually create this. I will account for the time of creating this, which I actually don't know how long that'll be. So let's time that just so we can see what that looks like. And we'll see how much cost we have just moving data around. And by the way, let's do this in the flag, otherwise well, that's kind of slow. 1.2 seconds to just create our data set. Okay. So it was 0.43 seconds to create our data set. The program's still running. Look at that. It's quite slow in some cases to move this data around. My goodness. My goodness. And you can see we still haven't got anything. Let's run this with just one process and see if that's a little bit better for our overall time. And that should be good. That should be good. We have one of those for each one of the processes. Why don't we have an overall time here? Let's just check one thing, make sure that we have. Okay, that's our overall time. So is it really still running, moving this thing around like that? My goodness. Let's make this thing a little bit smaller too. Whatever the case, we might need to refine our benchmark very slightly just to get this thing to print out properly. Whatever the case may be, it actually can be very expensive to move this data around. It's also quite clumsy because we have to use that multiprocessing.q. So maybe using the concurrent.futures might be an approach that we'll try. So what we're going to do is in the remaining time that we have, we're going to take our little block here that has our pandas code, and we're going to see if we can improve the speed of this using multiprocessing. Now, that doesn't mean that we cannot improve the speed of the other parts of the code. For example, loading the job results or loading whether the job succeeded or not with multiprocessing. We may find the results for that and the speed up for that is not too different from the speed up from threads. But I want to see what we can do with multiprocessing that we cannot do with the other approaches. In truth, the best version of this program, which we encourage you to try yourself and maybe to share their code with us, might involve some combination of multiprocessing, threading, and Asyncio. But to take us to the finish line, here's what we'll do. We will use concurrent.futures. We'll get a process pool executor. For our process pool executor, what we'll do is something like this. We'll set max workers equals 1 as the executor. Here we'll say grouped weighted, or this is a weighted mean on a group. So we'll make this a named function like that. What am I doing? Why wouldn't I just make that a sign like that? There we go. And then what we'll do here is the following. We're going to take our executor, we'll map to it. Here's our, and we'll talk about what we'll name that in a moment. We'll map to this thing, the weighted mean for each one of our categories. Now we're gonna have to do something slightly different here because these categories with the group by will give us the index and the group object. So here we'll just have to get the group object without the index. Like that, I believe. And here, this should then give us our results. We'll reconstitute this thing back into a pandas data frame or into series when we're done, so we can do maybe a concat of that. And then here, this should be our grouped weighted mean. Oh, we already have concat already. So there we go. So with just one executor, there's going to be some overhead time to just starting up that executor. So that's what we'll see if we just run one of these. And we can't, well, okay, let's make this named. You can see we get some issues with pickling things and moving things around. So I think that'll work. When you pickle things like functions, it'll appear to work. It'll appear like it's actually picking the thing, but what it's pickling is a reference to the name of the thing. So there's certain things you strictly can't pickle that are not even that exotic. For example, if you don't use functools.wraps on a decorated function, if you don't do this with wraps, you can't pickle the thing, because when you pickle a Python function, it doesn't pickle the bytecode, it just pickles the reference to the thing. So here, if you try and say from pickle import dump s, and this thing is decorated, this thing actually won't be pickleable. You get an error here. Let's see if we can get that to work. So that's why, one of the reasons why we use functools.s. But here, let's go back to our example here, and let's see, this seems to be relatively slow. Let's, of course, just force a rerun there. And what we'll do here is we're going to do one small thing. We're just going to do a .ilock and just get the first 1,000 rows just to speed this up. So we can see some initial results. Very good. This gave us a list. Okay, so we're going to do that ilock here, and we'll just do a regular slicing on this, get the first 3 of those, and get the first 1,000 rows. Okay, very good. And then finally, this gives us the result for these things. We'll have to reconstitute this into the data frame. So what I'll do is I'm just going to stick this into a list for now, because we'll have to actually set the index back up. And the index will, of course, be what the grouped values are. So it's 0.15 seconds with 1 worker. Let's see if 5 workers helps us. 0.17 seconds, it got worse. It's not unusual for these things to get worse. We really do need to measure where that sweet spot is. So maybe if we try this on more than the first 1,000 rows, it might be better. And maybe if we try it on more than the first data set, it might be better. But what we may discover is things like the process pool executor, in some cases, may improve our code. In some cases, may slow our code down. We always have to be aware of things like Amdahl's law. But I see that that brings us to the end of our session. I have a challenge for you. Take the example that we've put together and apply Asyncio, threading, and multiprocessing. Maybe try a producer-consumer approach, so it's not serially doing the first thing and then doing the second thing and then do the third thing, but interleaving them in some clever way, and see how much of a speed up you can get for all of the parts of this code. let us know in the comments or on our Discord channel. We'd love to see what you're able to do. I hope you have a better sense of how we can apply async I/O, threading, and multiprocessing to actual problems that we might interact with in our work dealing with APIs. With all of that said, that brings us to the end of this session and the end of this series. Thank you all for joining us, and we will see you all next time.